core challenge of Metal Slug on the Neo Geo isn't the action. It's managing extreme visual density within severely constrained memory architecture. We are analyzing 16-bit sprite manipulation under the limitations of the custom Neo Geo hardware, not just the fun of the run and gun. To understand this game, you need to look at how the PPU, the picture processing unit, was forced to render hundreds of distinct, high-detail sprites simultaneously. This wasn't a smooth 3D world. It was a masterclass in aggressively optimized 2D tile manipulation where every pixel had to be accounted for under strict frame budget constraints. The design philosophy here is less about fluid physics and more about aggressive data packing. We are looking at how the developers push the limits of sprite layering and collision detection on custom hardware to create relentless, high-octane chaos. This breakdown dissects the mechanics of that constraint, how memory limitations dictated level geometry, how projectile collision was calculated across tile boundaries, and what specific hardware workarounds allowed this chaotic engine to function flawlessly for decades. The fundamental constraint of Metal Slug on the Neo Geo hardware was not processing power for complex physics. It was managing visual density under a severe memory ceiling. To understand that chaos, we must first examine sprite and tile management. The PPU, the picture processing unit, was tasked with rendering hundreds of distinct entities simultaneously using limited video RAM. The game world is built on a rigid grid system. Every surface, every enemy placement is defined by these fixed map tiles. The developers couldn't afford dynamic geometry. They had to rely entirely on efficient tile-based rendering. This meant that the visual complexity, the sheer amount of debris, explosions, and characters visible on screen at any moment was a direct function of how densely the memory buffer could be packed. If we analyze the level design, you see an aggressive economy of detail. The environment isn't rich in subtle shading. It's rich in information delivered via distinct, high-contrast sprites. This wasn't artistic choice alone. It was a necessary optimization. Every sprite loaded into the VRAM occupied a fixed block, and exceeding that allocation meant immediate frame rate collapse. Therefore, level architecture became an exercise in aggressive data packing, using repetitive tile patterns to maximize visual impact while minimizing the memory footprint required for dynamic objects. This memory limitation directly dictates how we analyze collision detection. In this engine, physics is not continuous. It is discrete, calculated per frame against a fixed grid. Projectile interaction is the most telling example of this design philosophy. When a player fires, the system doesn't calculate true ballistic curves across a continuous plane. Instead, it checks for intersection against the underlying tile map structure. A bullet hitting a wall isn't a smooth, physics-based bounce. It's an immediate check. Does the projectile's bounding box overlap with the coordinates of the wall tile? This process is brutally simple. The collision routine operates on integer math against a defined grid. This simplicity is both the game's defining feature and its most exploitable weakness for advanced players. Because the system relies on this rigid boundary check, exploiting the geometry becomes an act of manipulating those exact coordinate boundaries. A player can exploit the inherent latency in the frame update cycle, the minuscule delay between movement input and the collision response, to ensure they clip through walls or target enemy hitboxes that are mathematically adjacent to the tile lines. The impact is immediate. True spatial awareness is sacrificed for speed. The game rewards players who understand the underlying math of the grid, rather than those who rely on smooth, continuous physical simulation. To understand why Metal Slug functions this way, we must step outside the code and examine the environment that forced those decisions, the development team and the Neo Geo hardware itself. Unlike titles on more standardized platforms like the PlayStation or N64, the constraints here were far more bespoke, creating a unique engineering challenge. The Neo Geo system was not built around a generalized, high-precision floating point architecture. It ran on highly customized 16-bit processors and specialized video hardware designed for arcade demands. This meant the developers weren't working within a mature SDK. They were operating with a specific set of undocumented or tightly controlled hardware limitations that shaped every line of code written. Development process became an exercise in constraint management. The goal wasn't to push the boundaries of what the console could do, but to extract maximum kinetic action from what it could manage. This led to design choices, like the rigid tile-based collision and the aggressive sprite layering we just discussed, that were not accidental aesthetic decisions, but rather necessary engineering compromises to ensure gameplay remained responsive and playable within the system's strict performance envelope. The result is a game defined by its limitations. The relentless pace, the exaggerated scale of the explosions, and the necessity for frame-perfect input are direct artifacts of forcing high-octane action through tightly constrained 16-bit architecture. When we look at the work done by the developers responsible for Metal Slug, the narrative shifts from pure mechanics to intentional design philosophy. They were not simply reacting to a standard SDK. They were operating within an environment defined by arcade demands and proprietary 16-bit hardware constraints. This context is crucial because it explains the inherent tension in the gameplay loop, the relentless, chaotic action versus the rigid structural limitations of the engine. The team's objective was clear: deliver high-velocity, screen-filling action that felt impactful on a dedicated arcade cabinet. This required prioritizing visual dynamism over complex, real-time physics simulation, a necessary trade-off dictated by the hardware budget. They understood that true fidelity wasn't in smooth motion. It was in maximizing the perceived chaos within the frame rate budget. Consider the enemy AI we touched upon earlier. It is not an advanced pathfinding algorithm attempting to optimize routes across a dynamic map. It is a highly optimized, state-driven system designed to maximize screen presence while minimizing CPU load. The developers utilized this limitation as a creative tool. They leveraged the fact that the hardware could handle simple, aggressive state changes extremely quickly, allowing for immediate, visceral reactions from the player, a direct translation of their intent into mechanical reality. Ultimately, the legacy of Metal Slug on Neo Geo is not just a collection of fast-paced levels. It is an artifact demonstrating how functional constraints force creative solutions. The developers didn't break the engine. They engineered around it to create a specific, high-energy experience that perfectly utilized the 16-bit limitations. We have dissected Metal Slug not as a nostalgic experience, but as a functional piece of 16-bit engineering. What we've established is that this game is a powerful case study in how extreme constraints dictate aesthetic and mechanical outcome. The Neo Geo platform, with its unique custom architecture, forced the developers to prioritize kinetic impact over complex spatial simulation. The result is a system where the limitations, the strict memory allocation, the grid-based collision, the frame rate-dependent rendering budget were not flaws to be overcome, but the very scaffolding upon which the gameplay was built. The brilliance of Metal Slug lies in its mastery of this constraint. It took the rigid rules of 16-bit processing and weaponized them. The developers didn't just create fast action, they created a highly efficient system where every bullet fired, every tile interacted, and every frame was an intentional choice made under severe mechanical pressure. When you look back at this title, do not focus solely on the visual spectacle. Focus instead on the execution. It is a perfect demonstration of how creative design can emerge directly from rigorous adherence to hardware limitations. It remains a benchmark for how powerful gameplay can be extracted from a tightly defined, constrained system. This is not just retro gaming, this is retro engineering.